networking has a lot of challenges. Synchronization is one of them. And to optimize the communications between systems, it has to work properly. So could you tell us a little bit about Deadaelus, why you just started this company, and what kind of solution are you coming up with? It's very unique.
Well, I've been working on distributed systems and large-scale systems for most of my career. And what we found is that there's some really deep problems that haven't been solved. And often it's easy to describe them as related to databases and in particular database transactions. But it turns out that this coordination problem of having multiple microservices all talk to each other in a way to achieve a common understanding of something is just a general problem in distributed systems. What we've discovered is that the way that we do networking today kind of thwarts the distributed systems programmer. Mm-hmm. All the programmers want you to do is for the packets to get there and to get them in order. So the network engineers give us this illusion of trying to do this with like TCP. It turns out that TCP only works for like file transfer. It doesn't work for rapidly interchanging information that you get on transactions. Now, why is that important? Well, it turns out that every database in the last few decades has had these hidden corruption of data structures. And many of them are silently corrupted. You couldn't talk about it in previous decades because you had to sign an NDA with your favorite vendor and you couldn't disparage their product or tell anyone about what wasn't working and what was working, otherwise you'd lose your discounts. But since many databases have now gone open source, and there are now dozens, if not hundreds, and some of them are very well known, several of the universities have been able to do, let's call them benchmarking on these kind of failures. And in particular, earlier this year, just a few months ago, there was a paper by the folks at the University of Waterloo in Canada that was called PNP, or Partial Network Partitioning. And it was all about how this peculiar problem of the network misbehaving causes these hidden data corruptions in the data structures, which then gets translated to the logs in the databases. So what we've got here is not just an existence proof, but concrete evidence that this is a pervasive problem that no one has solved. Part of the problem is no one has understood it before. And part of that is because all computer scientists are trained to think of things in a sequential order. It turns out that all human beings do as well. Like, we're trained to model our memory of the future and our memory of the past. And I intended to say that deliberately because it's just two models. In order for us to experience the present and then do what's right to enable us to avoid predators, to find food, to find a mate, and to plan for the future. Mm-hmm. And so that human neurology is built into the way that we think. The problem is, when you go into the physics and the mathematics of what we're doing, that irreversible notion of time from, infinite past to infinite future on a single line is a complete fabrication. It does not exist in physics. All the physicists know this. No one's actually got a better, a very sophisticated answer to this. At least one you can describe simply. The physicists have actually understood this for a long time. Over 100 years ago, Einstein proved that you can't have simultaneity. You can't have the same instant of time and the order of events are perceived by different observers, even in the simplest version of special relativity. So why do we think today we can synchronize clocks? Why do we think we can, read our watch, because it's, got a connection to a GPS satellite that's updating time here, or on the network, PTP or network time protocol or some other form of synchronous Ethernet or whatever else. Most of it is a complete misconception, because what's going on is all of those forms of time are a tree. And I mean a tree with a root and many branches. Mm-hmm. And so it's interesting because when you realize that, you say, well, okay, the engineering problem is then I have to pick my root. Now, of course, we pick our route as, GPS and whatever, is the source of GPS, which is a bunch of clocks, in the United States that are all synchronized and averaged in a way that, gives us this view of time that is, that gives us the ability to do GPS navigation to within a few feet instead of a few kilometers. Because if you didn't include the general relativity and the special relativity effects in the GPS calculation, you'd get lost. You wouldn't just be taking the wrong turn, up the street. You'd be in the wrong state.
Exactly.
And so it turns out that most people don't understand the subtles of that problem. Now, I'm only talking about general relativity and special relativity here. It turns out it gets even worse when you deal with quantum mechanics. And so it turns out the problem, and computer scientists have dealt with this many times, that it's like, what is causal ordering in a computer? Well, the causal ordering, what does Winston Churchill call time? He said, one damn thing after another.
Yes.
And it means that one damn thing after another in Alice's computer is not the same as one damn thing after another in Bob's computer. Mm-hmm. And that is something that is an enigma. We don't understand it, and engineers certainly don't understand it because they're trained to think sequentially, especially with languages like C and JavaScript and any of the other languages that you might like. And so the sequential thinking leads us astray when we try to think about concurrency. Now, everybody knows this is a problem. Not many people actually understand it, and you could say that we as a society actually don't understand it at all, because we don't have a replacement theory that tells us what time really is, because it's the biggest enigma on our planet right now, in our society. So there you go, there's a problem there. There's evidence for it in all of this corrupted databases. So what if you could think about time in a different way so that you could engineer a protocol that gave you essentially the characteristics of entanglement? We like to say that we take the spooky out of action of a distance. Mm-hmm. And what I mean by that is we carefully control the events that happen inside a single Ethernet link. You might say, well, that's not so difficult to understand, is it? Mm-hmm. If I send you an Ethernet packet and I say, just transform it slightly, like swap the 2 8 characters around in the byte, in the word, mm-hmm. and then send it back to me, and I do the same, then there's no change in the information. So there's no point in you telling your, host processor, miles above you, that anything happening. Mm-hmm. Which is saying, hi, are you there? Yes, I am. Hi, are you there? Yes, I am.
Okay.
So are you there? Yes, I am. That protocol is actually a very quantum-like protocol. We try to distinguish between the physics of entanglement and the mathematics of entanglement, because if we just make this Ethernet packet that's circulating do this thing, then it's going to recognize that the question it asks, are you there? Yes, I am, is going to go on forever. We call it in perpetuity. So, where are we? We basically now said, well, if you could do that kind of game on a single Ethernet link, then can you use that for a computer science concept called liveness? Because in distributed systems, there's really kind of like 2 things that we worry about. One of them is safety. Did the right thing happen correctly? And the second is, did it happen eventually? Which is liveness. And so it turns out that these 2 problems have been well articulated in computer science, but they've never been mixed with the physics. Because computer scientists think in terms of this one damn thing after another, because that's the way they taught sequentially to program their computers. Mm-hmm. So what we've got here is an understanding about how we can measure and organize this activity inside an Ethernet link. And so we've said, well, we're engineers, we can design protocols that are hidden in this link, that are, A, they're invisible, you can't see them, and B, they are indivisible. They can be atomic. Mm-hmm. So instead of having 2 computers, Alice and Bob, where each of them can independently do a compare and swap, for example, or some other kind of RDMA action that, it's like, do this for me and tell me when you've done it. No, that's being done in the memory of each computer. What if you could do a tick-tock, liveness between 2 systems, and then the link itself becomes a computational object. Now we're starting to deal with the raw essence of what happens in networks, which is packets get lost, they get duplicated, they get delayed, they get reordered. Those behaviors are because of the way we grew up understanding networks, and it was a great idea to do that a long time ago. But unfortunately, it thwarts the programmers, the distributed systems programmers, who just want their packets to get there in order. Because if you duplicate the packets, you now have to force their operations to be idempotent, as they say. And idempotency is a very tricky thing to get right in a distributed system. We know it doesn't work. And the holy grail in distributed systems is called exactly once semantics, which means if you do something, it can't be done more than once, and it can't be done less than once. And it turns out there are different protocols and different databases have different variations on this, but no one's been able to achieve exactly once. Some of them achieve at least once, and some of them achieve one or more, but they can't guarantee it's exactly one. So that holy grail of what the programmers really want to have is the problem that we're trying to solve at Deadaelus. Now, a side effect of solving that problem is that we also solve another set of problems, which is the meltdown that happens in a data center called gray failure or metastable failure, which you hear a lot in recent papers in the last 12 months or so, where the system goes into this degraded performance state and it stays there, it doesn't get out. That's what they mean by metastable. It's either in this state, performing, or it's in this state, not performing. And no matter what you do, unless you reboot all your systems, it can't get itself out of that system. Gossip systems tend to have that problem. We've seen those kind of meltdowns in Amazon, for example, and many other data centers that use those protocols. But it's not just gossip. It's the idea that you can drop and delay and duplicate and reorder the packets at will. So what we're trying to do is put together a consortium of distributed systems programmers who are thoroughly familiar with this problem and are really tired of having to deal with it. And the people who build and architect the functionality inside SmartNICs. We think that if you bring those two people together with an API that allows you to delegate functions to the SmartNIC, we think that you can do something profoundly more interesting to solve these problems we have in today's data centers. And so that's why Deadaelus exists. Deadaelus, by the way, is the Greek mythology of the architect of the Athenians, and he was the designer, the architect of the labyrinth, in which they imprisoned the Minotaur. And of course, our hero Theseus had to go in and kill the Minotaur and be the hero of the Athenians in a different kind of way. But this idea that you can design an impenetrable, inescapable, labyrinth is really what the company is all about. And obviously, you can see that beyond just the do things invisibly and indivisibly, in a transaction sense, there's also a lot of opportunities to build a much more secure network enclave as well.
Very good. Well, thanks for providing an overview of Deadaelus and some very challenging problems.